Okay, so in this video, what we're going to do is we are going to make some buffers. This is something I have continuously seen people struggle with. I struggled with it too at first until I started to understand what was happening. All right, so our goal in this problem is we're going to make a 0.05 molar sodium phosphate buffer, a total volume of 100 milliliters, and we want this buffer to be 7.4, a pH of 7.4. And we're going to do this by using the buffer pair sodium dihydrogen phosphate. This is the molar weight of that. And disodium hydrogen phosphate. This is the molar weight of that. Now, you will, if you're on a test, you're going to be given the pKa, but if not, you can just look it up. These are known values. So this is the pKa of our weak acid, which is going to be the sodium dihydrogen phosphate. And so the very first thing we're going to do, step one, is you're going to find the ratio of the conjugate base to the weak acid, and then we're going to find the amount of moles needed. Okay, so we're going to use Henderson-Hasselbalch to find the ratio that's needed. So you plug in your desired pH, which is 7.4, the given pKa, or the one you look up, plus log 10 of that ratio. Then we're just going to do the algebra here. So you're going to undo the log, right? You're going to say 10 to the 7.4, which is pH minus pKa, equals your ratio. The ratio is going to be 1.54882. Now let's think about what's going on here. Because this is a ratio and it's greater than 1, that means that our conjugate base is we're going to need more of that to get to a 7.4 than we would of the HA, right? Because it's 1.54. You can also know that even before we begin. So this is the pKa, so the pH that half of the weak acid is protonated and deprotonated. And this is 7.4. Our desired pH is more alkaline than the pKa, which means we will need to add more of the base to adjust for the lower pKa value of this weak acid. So again, let's think about what these numbers mean. Okay, because we have two unknowns here, we're going to need two equations. And so we're just going to use this, right? This can be an equation for us. We can say 1.54 times HA equals A minus. Well, then another equation, you can see that our total moles that we want is 0.005 moles total. Now, how do we know that? So remember, our total volume that we want to make, we only want to make 100 milliliters of this buffer. We don't want to make a whole liter because that's just a lot of buffer. And so 100 milliliters, you're going to turn that into liters. And I don't know why I have well, whatever. It's supposed to be 10 to the negative 3. This right here. Oops. Oh, no, lies. This is 1,000. I was like, what is that? Okay, 1,000 milliliters equals 1 liter. There we go. And then you're just going to turn that into moles, and you're going to find that it's 0.005 moles. So you just take volume, turn it to liters if it's not already in liters, and then multiply it by the desired molarity of your solution, which is 0.005 moles, molarity. And so you're going to moles per liter, because that's what molarity means. Okay, moving on. So that's the total moles. So then we're going to take 1.54 HA that we found with our Henderson-Hasselbalch plus HA. So why are we saying plus HA? Well, this is equal to our conjugate base. And so if we think about it, A minus plus HA equals the total moles, right? Because these are our two components that are going to be in our buffer, okay? So what we're going to do now is we will just add that up. Well, remember there's an invisible 1 right here. So 1.54 HA plus 1 HA is going to be 2.54 HA. And that still equals total moles. Then you just solve for HA algebraically. And HA equals that. All right. So then what you're going to do is you're going to plug this value into this equation, because now we have HA. And now we can solve for A minus, which is our conjugate base. And so we're going to have 0.003. And indeed, we are going to have more of our conjugate base than weak acid, which is what our ratio told us, which is also what we logicked out up here. Now, just to make it easier, you don't have to do this part, but we're going to turn moles to millimoles. It's just easier for some people to deal with nicer numbers. And so there's 10 to the negative 3 moles in 1 millimole. And then you just solve for that. That's how many millimoles of your conjugate base. This is how many millimoles of your weak acid. Then what you're going to do is you're going to find the grams of each using that molecular weight that you were given. So you take the amount of moles, multiply it by grams per mole, and you don't want to use your millimoles for this because you want the moles to cancel, so you get grams, and you'll get 0.8 grams. Then you're going to do the same thing for your weak acid, and you're going to get 0.27 grams. And that is how you make a 100 milliliter 0.05 molar sodium phosphate buffer using that buffer pair.